Dr. Lisa Alexander's research has focused on our understanding of how climate extremes are changing globally and over Australia. Her key contributions with marked policy relevance include providing convincing evidence that future changes in the frequency and intensity of heat waves in Australia will be strongly dependent on the amount of anthropogenic greenhouse gas emissions. Dr. Alexander, congratulations. Now I'd like to invite you to talk to us about how future greenhouse gas emissions will affect Australia's climatic extremes.
Okay, like the other speakers, I would really like to thank the Academy for this honour and also for allowing me to present the work that I really love doing and that I've done with many, many collaborators over many years. And that work really has involved looking into the variability of climate extremes, both from a historical perspective and also to look into the future of what might be policy relevant for the future of climatic extremes. So I probably don't need to tell everybody in the audience, and anyone who's lived in Australia for any length of time will know, that this is a land of droughts and flooding rains. But it's also home to a lot of other climatic extremes that affect its people and its unique natural environment, and these include heat waves and bushfires and cyclones. It's also got many and varied different climatic zones, as we know. And to complicate matters even further, there are many drivers of weather and climate extremes, both oceanic and atmospheric drivers. These drivers act over days, different timescales, through to seasons, years, and decades and longer. I'm not going to talk in great detail about every of them, but I will say talk a bit about one, which is the El Niño Southern Oscillation. And it's probably one of the most important coupled oceanic atmospheric coupling phenomenon that we have globally, certainly on interannual timescales. It's characterized by anomalous warming and cooling of the ocean surface in the Pacific. It exists in two predominant phases, which are El Niño, which you'll see here, where we get anomalous warming in the eastern Pacific and cooling in the western Pacific. And on the opposite phase, we have La Niña, where we get the cooling in the eastern Pacific and the warming in the western Pacific. And at other times, we have, this is in a neutral phase. It's driven primarily by intensification and weakening of trade winds, and also this east-west circulation pattern known as the Walker circulation. And you can see that as this pattern weakens and strengthens, this depends where we have convection forming and rainfall. So what does it actually do and how does it affect climatic extremes? Well, I've just got a couple of examples here. I'm going to show you first what the predominant patterns are for extreme temperature events and extreme rainfall events globally when we're in the pattern of La Niña. And what you can see is during La Niña, we usually have a couple of degrees cooling of quite a few regions of the globe. And also, we have wetter than normal conditions over many regions. And if we look at that for the El Niño portion of the phase event, so you can see that the pattern's actually almost the opposite. And if we focus in on Australia here, for example, we get a couple of degrees cooler during a La Niña event in temperature extremes and a couple of degrees warmer in the hottest days of the year during El Niño events. That's also manifest in the wettest days of the year, where it's much wetter than average during La Niña and much drier than average during El Niño. So that's sort of what the patterns look like, but how do we know what's driving these particular patterns? And one way to do that is to look at climate models. Now, these are complex numerical models which simulate our understanding of all of the physical laws that we understand about the weather and climate system. There's currently over 30 of these models globally from many different modeling centres. And over the years, these models have been developed to improve their physical schemes and also to include things like biology and chemistry. Do these models actually do any good, and do they actually look like the observations? Well, you can see that in a sort of previous generation of climate model, the top row are actually the observations here, where we're taking we're taking El Nino events away from La Nina events. And you can see that in this sort of earlier generation of climate model, while the pattern is broadly similar, you can see that this anomalous cooling is actually too thin. It doesn't go far enough north and south, and it extends too far to the eastern Pacific. In terms of the impacts over land, which is what's sort of most relevant for a policymaker, you can see that in the observations, we do get some significant gradients according to whether we get positive or negative phases of this ENSO phenomena. But in this particular case, this particular global climate model just really can't capture some of this. In a later generation of exactly the same model, we can see that now later generations are really starting to get better representations of the patterns that we see in the observations. And also, and now you can see that if we focus in on North America, for example, you can see that it's starting to get a bit more similar to the observations. And even over Australia, you can see that this particular model appears to be doing a slightly better job. And as it turns out, having all of these multiple climate models actually is generally better than any individual one. And when we look at simulations, in this case, of the number of warm nights that you get annually in Australia, all of these different coloured lines represent multiple simulations from multiple climate models, and the black line represents the observations. And you can see in this case, the observations sit nicely in amongst all of the simulations. Also, when you look at the trends over time and you use the multiple models, you can see that you actually get quite a nice representation of this very significant increasing trend that we've seen in warm nights in Australia over the last 50 years or so. So what's causing these changes we've seen? Well, the other great advantage of a climate model is you can perform experiments where you include or exclude certain phenomena and drivers. In this case, what we can do is we can look at just the natural-only drivers of the climate system as we understand them. And as we understand them, and I'm just showing a couple of different climate models here, these are the observations. This is where the observations lie. And this dotted line is where the, if we only include our understanding of the natural variations in climate, we cannot explain why we've seen the increasing trend that we've seen in warm nights over Australia over that period. And it's only when we start including emissions that we've seen increases in greenhouse gases and changes in sulfate aerosols that we actually start getting a better representation of how the observations actually look. So we can't explain these changes that we've seen unless we include all of the forcings as we understand them. However, the pattern is much more complex for these very heavy precipitation events, and that's because there's a much smaller signal-to-noise ratio in precipitation compared to temperature. So while we do see some evidence of a better representation when we include all the forcings, we couldn't rule out that the changes we've seen in precipitation over the last sort of half century are simply due to natural variations in climate. So a question I get asked a lot is when there's a significant event like there was in the severe flooding in Eastern Australia in 2010-11, is can we attribute these events to climate change? Was actually a very difficult question to answer, especially in Australia because of this large natural variation that we have. And in fact, if we do try and model this in terms of trying to say what's the increased risk of these type of events under increased greenhouse gas emissions, there's actually no separation really here between the two distributions. Some evidence that we are seeing an increase in the most extreme events, but we can't statistically separate these two distributions. What is quite clear, though, is that we can extract the La Nina signal from this. That means that the dominant driver of extreme rainfall in Eastern Australia over the last 100 years or so is from these La Nina events. Of course, having an absence of evidence doesn't imply evidence of absence of an anthropogenic signal. It's just that it's much harder to detect. Now, I've spoke a bit about what our past observations have been, and now I want to just very quickly look at what some of these events might look like in the future under increases and changes in greenhouse gases. Now, I'm very quickly just going to go through a couple of different scenarios. One is where we have a low population growth and we have less fossil fuel use. And another one is where we have high population growth and very intensive fossil fuel use. Now, if we look at that for the future for Australia, we can see that irrespective of the scenario we use, we do see an increase in temperature extremes across the continent. And you can see that as we increase our greenhouse gas emissions, we also see an increase in the magnitude of those extreme events. And if we look at a measure of drought, which was in the title, we can see that in general we are going to see an increase in the length of droughts in the future, although you can see that there's much greater uncertainty amongst the different climate models. And when we look at our flooding rains, again, because of this low signal to noise, while there is an indication that we will see an increase in these flooding rains, again, the models are much wider in their uncertainty. So I won't go into this in any detail, but just to say that those results helped to formulate the Intergovernmental Panel on Climate Change Special Report on Extremes, which happened last year. And just my conclusions are what I've already said, but I just wanted to reiterate one fact, which was really decisions have to be made on these issues irrespective of our certainty that we have in what will happen with changes in either temperature or rainfall extremes or any other type of extremes. And I think that we can play a role in highlighting where we have confidence and where we have uncertainty. Thank you.
Are there any questions or comments for Dr. Alexander? Steve.
Thank you. This is Steve Powers from the University of Western Australia. As well as being a scientist, I have a farm right in the middle of the Western Australian wheat belt, and it seems like we have nothing but droughts and frosts and other adverse events. But in terms of, especially of your final comment, and you quite clearly showed the increase in temperature, which we've definitely experienced, and I know we're only talking in the short term, but what we have also seen, at least anecdotally, is a significant increase in the number of frosts, yes, which seems to be at odds with this. And it must be difficult for policymakers when being told that temperatures are going up when another sector of society, my sector of agriculture, farmers are saying the number of frosts are going up. It's not getting hotter, it's getting...
Well, it's actually a very, very good question. And actually things like increases in frosts could actually be linked to decreases in the amount of precipitation. So we could see a change in one extreme, which are going to impact another one, and then you might start getting these somewhat different curious signals that you're seeing, and trying to explain that to a policymaker, as you say, is incredibly hard. But there are ways that we can explain it, which is a change in one extreme could lead to a change in another, which is opposite from the change we expected. Yeah.
On that note, could you please join me to thank Dr. Alexander?